Welcome to the video. In this video, we are going to look at problem number 3 of chapter 23. There's a diagram that goes with it, and that is figure 23.10. From the description, you can see that there are a couple of cases. In each case, the electric field is given, and we are supposed to do two calculations. The first calculation is to find the electric flux through the right phase, and that is the phase on the right hand side. And in the second part, which is actually stated in part D, and we are supposed to find the total flux through the cube. So let's take a look at the first case, or part A, where the electric field is given as 6.0 along the x direction. In the diagram, I have also indicated the phase, that is the right phase. Now, this right phase corresponds to the right phase in that first sample problem. As you can see here, the direction of the surface element dA is pointing outward or horizontal to the right. Coming back to problem number 3 and look at the diagram, and we can see that for that right phase, the direction is horizontal to the right, and in this case, along the y direction. And therefore, the surface area can be written as the magnitude of the surface, along with the unit vector j. And between the two vectors E and A, we can form a dot product, which is the electric flux, and the value of which should be 0. You can arrive at the value 0 by either using the formula or just by looking at unit vectors. Since I hat and j hat are perpendicular to each other, the dot product between them should be 0. Moving on to part B, where the electric field is -2 followed by a unit vector j hat, and the surface area is still the same as before. And once again, between the two vectors E and A, we can form a dot product to obtain the electric flux. And you can do the calculation using one of the formulas. And in part C, we have an electric field that has both an x and a y component. You can do it either using the formula in the book, or you can do it using vector algebra. I'll do it using vector algebra. By using the distributive law, we can expand the dot product. Notice that in that first term, we have a dot product between I hat and j hat. And once again, since I and j are perpendicular to each other, the dot product between them should be 0. And in that second term, we have a dot product between j hat and j hat. Since j hat is a unit vector dotting itself will be equal to 1. And the result is just the product of the two magnitudes. And now let's move on to D. In part D, we're supposed to calculate the total electric flux for the three cases that we have looked at. So let's go back to part A, where the electric field has a magnitude of 6 and is pointing towards the x direction. In this new insert here, I have added the vector for the electric field. A field vector can also be drawn on the other side of the cube. Here we're going to use the terminologies introduced in the previous video, titled The 3 Special Cases. If you have not watched that video, please do that first. So, if you look at the electric field in the front, that electric field is piercing outward, resulting in an electric flux that's positive EA. And on the other side of the cube, the electric field is piercing inward, resulting in an electric flux that's negative EA. On the other four sides of the cube, the electric field is just skimming on the surface, and therefore the resultant electric flux will be 0. And therefore the total electric flux for the whole cube will add up to 0. And now let's move on to part B. In this new insert, we can also draw the electric field vector. But notice that this time the electric field is pointing in the negative y direction. And just like before, the electric field on the right hand side is piercing inward, resulting in an electric flux that's negative EA, whereas the electric field on the left-hand side is piercing outward, resulting in an electric flux that's positive EA. And on the other four sides, once again, electric field simply skims on the surface, resulting in an electric flux of 0. And lastly, we are supposed to calculate the total electric flux using the electric field given in part C. And this electric field is a little more complicated. We can use the procedure as we did before. However, we can apply the Gauss law to conclude that the total electric flux will be 0, regardless of how complicated the electric field might be. Of course, we have not introduced the Gauss law yet. That is actually the topic of the next video. For now, let's just jump to the conclusion that the total electric flux is 0. And we'll come back to revisit this issue after we complete the next video. And that completes this video.